Welcome to the Explainer. So today we're going to talk about a really big shift in how AI models get trained. It's this whole new philosophy that basically says, hey, what if we traded all this complexity for some really elegant, provable math instead? All right, let's really get into this, because there's a brand new approach called LeJEPA, and it's built entirely around this one question. It completely challenges this idea that we have to keep, slapping more and more complicated patches onto our AI systems to make them work. So to really get what LeJEPA is all about, we gotta first talk about the family of AI models it comes from. They're called JEPAs. And honestly, the basic idea is pretty simple. Imagine you show an AI two different but related views of the same thing. Like two different close-ups of a cat picture. Then you train it to predict one view just by looking at the other. This little game forces the AI to learn what's actually important in the image, the essence of catness, if you will. Okay, but here's where things get messy. What's so interesting is that actually training these JEPAs has turned into this crazy game of whack-a-mole. Seriously, researchers have to pull out this whole toolkit of super complex, fragile hacks just to stop the models from completely failing in the most basic ways. And the number one problem all these hacks are trying to fight, it's something called representation collapse. This is basically where the AI gets lazy. It figures out a useless shortcut, like mapping every single input, every picture you show it, to the exact same internal idea. It's like, technically it's not wrong, but it hasn't learned a single useful thing about the world. So with all this mess, a bunch of researchers finally just stepped back and asked a really fundamental question. Like, instead of adding yet another patch, is there a cleaner, more elegant way to build these things? A way to solve the problem from the ground up without all these fragile, complicated parts? And yeah, that's exactly what they did. They decided to stop playing whack-a-mole. Instead, they went back to first principles to find a solution that's based on solid, provable math. Something that doesn't just work by luck, but is designed to be the best possible solution. And this led them to a really crucial question. It sounds almost philosophical. What is the ideal shape for an AI's knowledge? Like, if we could mold all the information it learns into some perfect, super versatile structure, what would that structure even look like? And believe it or not, they actually found an answer, a provably optimal one. The big aha moment came straight from mathematics. They identified this one specific shape, a distribution that is just perfectly suited for a model that needs to be ready for, anything you might ask it to do later. So what is this magic shape? It's called the Isotropic Gaussian. Now, the easiest way to picture it is to imagine a perfectly round, totally symmetrical cloud of data points floating in space. It's the most neutral shape information can take. It has no weird biases, no stretched out parts, and that makes it perfectly prepared to handle any new task you throw at it with the least amount of error. And you can really see the difference right here. On the left, you've got this lopsided, anisotropic shape. It's brittle, it's really good at one thing but terrible at everything else. But on the right, that isotropic shape, it's perfectly balanced, it's stable, it is robust, and just ready for anything. Okay, so we've got our goal. We want to gently nudge the AI's giant cloud of knowledge until it looks like a perfect sphere. Simple enough, right? Well, not so fast. How in the world do you check for a perfect sphere in a space that has thousands or even millions of dimensions? It's pretty much impossible. All right, this is where the real magic happens. Let's talk about the tool they invented to solve this impossible problem. It's called SIGReg, and it is such a brilliantly simple solution. The big idea is, instead of trying to look at the whole crazy high-dimensional shape at once, it just looks at thousands of simple, one-dimensional slices of it. So here's how it works, and it's actually beautiful in its simplicity. First, you take that complex data cloud from the AI. Then, you project it onto tons of random 1D lines. Imagine shining a flashlight on it from all different angles and just looking at the shadow. This gives you thousands of simple 1D distributions. And then, you just check if each of those simple shadows looks like a perfect bell curve. If every single slice looks right, then you can be sure the whole thing has the perfect shape. It's genius! And what this does is it completely bypasses one of the absolute biggest headaches in all of machine learning. It's called the curse of dimensionality. That's just a fancy way of saying that things get exponentially harder to deal with the more dimensions you add, while SIGReg just sidesteps that problem entirely. So when you put it all together, what do you get? You take that standard JEPA learning task, predicting one view from another, and you add this incredibly powerful SIGReg shaping tool, and boom, that's LeJEPA. It does two things at once. It learns useful stuff about the world, and it makes sure all that stuff is organized in the absolute best way possible. And the advantages in the real world? They are huge. You can just throw out all those old, fragile hacks. No more stop gradients, forget about teacher-student networks. It's stable, it's reliable, and get this, it just works right out of the box on over 60 different AI architectures and even on totally new kinds of data. And all that crazy complexity from before, it gets boiled down to just one single dial you have to turn. Seriously, just one parameter that you use to balance the two jobs, the prediction task and shaping the knowledge into that perfect sphere. That is it. Okay, but this is the million-dollar question, right? Does all this beautiful, simple theory actually lead to better results in the real world? I mean, can a small, specialized model trained with this super simple method actually go head-to-head with a giant, general-purpose model and win? Well, just take a look at these results. The answer is a huge, resounding yes. This is a classic David versus Goliath story. On a specialized dataset of galaxy photos, a little LeJEPA model trained on just 11,000 images doesn't just compete with, it handily beats massive models like Dino V2 and Dino V3. And those things were trained on hundreds of millions, even billions of images. It's kind of mind-blowing. And this chart just makes that victory crystal clear. I mean, look at that gap. We're not talking about a small win here. This is a major outperformance. It proves that a smaller, focused model that's trained the right way can absolutely be more powerful than a generic giant. So let's zoom out for a second, because LeJEPA isn't just another new model to add to the pile. This is really a victory for a whole new philosophy in AI research. This result is a signpost pointing to a different way of doing things. So why does this actually matter? Well, for three huge reasons. First, it's a massive win for elegant theory over just messy brute force hacks. Second, this helps democratize AI. You don't need a supercomputer and a billion images to train a world-class model anymore. And third, it makes training way more reliable. The numbers you see during training actually predict how good the final model will be, which is a huge deal. So really, the big takeaway is this. When you move away from just cobbling together ad hoc solutions and instead start with elegant theory, you end up with something that's simpler, more stable, and often just plain better. It's a perfect case study for how deep understanding beats brute force every time. And that really leaves us with a powerful question for the future of AI, doesn't it? If LeJEPA proves that the best hack is to have no hacks at all, it really makes you wonder, what other huge, complex problems in AI are just bogged down in clever tricks, waiting for someone to come along and find the simple, fundamental solution that changes everything?